I guess we know all about the four conic sections, eh, Charlie?
Right, Ed. Now if we can just put them to some practical use.
Now we can tie the four conic sections together. Placed so they all have the same vertex, there is a single equation that describes them all. Different values for the Greek letter epsilon produce the four conic sections. If epsilon is 0, then the equation represents a circle. We can confirm this with a little rearranging. Epsilon values between 0 and 1 produce an ellipse. A lower value, such as 0.1, describes an ellipse that is almost a circle. A higher value, and the ellipse is more elongated. The epsilon value measures the curvature and is called the numerical eccentricity of the conic. An eccentricity of 1 corresponds to a parabola. And greater than 1, a hyperbola. Similarly, the eccentricity of a hyperbola determines how straight the curve is. Some of the most important applications of conic sections arise from their curvatures. These unique shapes reflect light and sound waves in distinct patterns. The circle is fairly obvious. Standing at the center of a circular foyer, your voice projects in all directions. But each point on the circular wall reflects the sound back to the center. If the ceiling is spherical, the sound will return with even more reinforcement. The ellipse has two foci, and rays emanating from one focus bounce off every point on the wall to the other focus. This occurs vertically in the Paris subway system. Some of the stations have elliptical shapes, and it's possible for two people to stand at the foci. Their voices project in all directions, but the elliptical roof converges all the sound toward the opposite focus. They can speak in whispers and still communicate effectively. The parabola also has a unique curvature. Parallel rays of light or sound all bounce toward the focus. This is the fundamental principle behind the dish antenna and the reflecting telescope. Both use a three-dimensional parabola called a paraboloid. The telescope's mirror can be made by spinning a container of plastic resin. The resin sets in the shape of a paraboloid, which can be coated with metal and polished. Situated at the base of the telescope, a paraboloidal mirror concentrates the incoming light to a central focus. The same principle is used in reverse in the headlights of an automobile. The bulb is situated at the focus of a paraboloidal mirror. Although the bulb projects light in all directions, the mirror redirects the rays to come out in parallel. Some headlight designs have now been modified to take advantage of the reflective property of the ellipse. A small ellipsoidal mirror converges the rays onto a focusing lens, which in turn emits the rays in parallel. Without the need for a wide paraboloidal mirror, the result is a powerful headlight about the size of a business card, a sleek companion to the latest aerodynamic car designs. The hyperbola has many applications as well, although they are somewhat more difficult to observe. For example, the sonic boom of a jet aircraft is a shock wave shaped like a cone. The intersection of the cone and the plane of the ground forms a hyperbola. The sound of the sonic boom is heard at every point on the curve at the same time. Hyperbolas also play a role in the space program. Interplanetary probes change direction when they fly past the planets. The probe approaches the planet virtually in a straight line, but the planet's gravitational field pulls the probe into a curved path. The hyperbolic trajectory is precisely calculated to stay far enough from the planet to avoid being locked into a permanent orbit. The probe is simply diverted to another direction. The hyperbola's shape also has a unique reflective property. A light or sound at the focus reflects in a radial pattern. The rays appear to emanate from a point behind the hyperbola. With such diverse applications, conic sections have secured their place in history.
Are we all set, Ed?
Sure, Charlie. We've got the circular deck, the ellipsoidal headlights, and the paraboloidal antenna.
Don't we have a hyperbola anywhere?
You bet, Charlie. Look, our trajectory will accelerate us around the sun in a hyperbolic path.
All right, let's go. Kick in the hyperwarp, Ed.
Okay, Charlie. I guess it is time to go home.